Hi students, in this part we'll discuss about the capillary tubes and capillarity action. First we'll see what is actually capillary tube. Finely bored means they are smooth from inside. Finely bored narrow tubes open from both sides. They are said to be capillary tube. Like you have the pen, so only the envelope of the pen or the refill you can take and you remove that nib from the refill, and only a plastic tube, very narrow tube, that can be considered as a capillary tube. Capillary tube is going to be closed, open from both the ends, right? Any tube like this, it is a capillary tube, cylindrical tube, open from both the ends. And this must be narrow, means it has not to be wide. Its radius is approximately of the order of 1 mm, 2 mm, 3 mm you can take. Now, why only narrow? Why this radius has to be small? That we'll see, and what is capillarity action, that also we are seeing. When we dip this type of tube, open tube, into some liquid, then liquid will rise in this tube or fall in the tube. Means if we have a tub of water, say, or some liquid is there in this tub, and we dip a tube in this capillary tube, then liquid will rise up to here, above the level of water. So liquid is rising in the capillary tube. For some other nature of material of tube, this is also possible that liquid is not up to here, rather the liquid is only up to here. Means liquid level falls. When we insert a capillary tube into a liquid, then liquid level may rise or fall in the tube. This rise or fall of the liquid in the capillary tube is termed as capillarity action. The rise or fall of liquid in a capillary tube this action is termed as capillarity action. Liquid will rise in the tube or fall in the tube. It depends upon the nature of the material of the tube and the liquid. So rise or fall depends upon the pair of liquid and tube, means tube is made up of water, and it also depends upon the contact angle of this pair. It also depends upon the contact angle of this pair. Now, why the liquid level is rising or falling, that I am explaining you on the basis of the forces from the mechanics point of view. Now, let us consider we have dipped one capillary tube into the liquid. Then, depending upon the contact angle of the liquid and this capillary tube solid surface, liquid meniscus will, shape of the meniscus will be decided. Let us say the contact angle is less than 90, so the liquid meniscus is concave up. Liquid meniscus is concave up. Now, here the pressure is P0, open to atmosphere. And due to the excess pressure across a curved surface, On the concave side pressure is more. So here the pressure is less than P naught. Is less than P naught. So you can say here it is P naught. Pressure on concave side is more than the pressure on convex side. So here P naught is more than this pressure. Surface tension force is acting. If I say this is the shape of the meniscus, the surface tension force is acting. Now this surface tension force will, there is a pressure difference. Surface tension force will pull it upside. Surface tension force will pull it upside to make the, at this point pressure has to be atmospheric. Here it is P naught, same height level, so here it has to be P naught. But because of the surface tension, it appears it is less than P naught. So to equalize the hydrostatic pressure, this surface tension force will pull the liquid up. It pulls the liquid up and it comes, say, up to this height. Say it comes up to this height. And say this height is H. Then here the pressure is P naught. Due to the pressure across the curved surface, pressure will become here P naught minus 2s by r, where r is the radius of this meniscus. I will tell you everything. We are moving in. Now the hydrostatic pressure, here pressure increases by rho hg. So the pressure here will become P naught minus 2s by r plus h rho g, and that has to be equal to the atmospheric pressure P naught. If liquid won't be rising, then here pressure cannot be P naught. So the pressure difference is arising due to the curved surface of the meniscus. To equalize it to the hydrostatic pressure, the liquid has to rise. So this way we can explain the liquid is rising. So we can say directly also up to what height the liquid has been raised. So here directly if I see, I can say P naught is equal to, P naught is cancelled. So rho g h is equal to 2s by r, and we can say h is equal to 2s upon r rho g, where r is the radius of meniscus. Right? We can explain the things in other way also. I am going to explain. Now r is the radius of meniscus I am writing, and let us take here capital R is the radius of the tube. Radius of tube. Now radius of tube and radius of meniscus need not to be same. They may be different. Now we will try to understand all the things in very simple way. Right? Now, let us say liquid rises to a height h, then this particular part of the liquid, weight of the liquid is balanced by the surface tension force. Now, surface tension force is S into 2 pi r in this direction. This is r. This is r. And contact angle is theta. Then this component of the force comes S into 2 pi r cos theta. And this is balanced by the weight of this liquid. Now weight of this liquid is rho into pi r square h into g. So here we got h equal to 2s cos theta upon rho r rho g, r rho g. 1 r cancel, y cancel, 2s cos theta upon r rho g will come downside. Now earlier what I have written, h equal to 2s upon r rho g. Now this r and this r is having a relation. This is the most important point to understand. Please see it carefully. Theta is the contact angle. Theta is the contact angle between this liquid and this solid. Now, if I draw a separate diagram, meniscus is coming like this way. This distance is r, radius of this tube is r. Now, this meniscus, if I make a complete bubble drop, it is coming like this. This way meniscus comes. Center of the meniscus is here. Center of the meniscus. This distance is r, capital R, radius of the tube. This is the radius of meniscus. Radius of meniscus. Radius of tube. Surface tension force is acting in this way. This angle is theta, contact angle. 90 minus theta. This angle is also theta. Radius of the tube, radius of the meniscus. So here we can have r cos theta is equal to r. So if here I will substitute small r, it can be written as capital R upon cos theta, capital R upon cos theta, and I will get the same thing. So we can write it as 2s upon r rho g also, r rho g also. Here r is the radius of tube. Here r is the radius of meniscus. Radius of tube and radius of meniscus are two different things. Radius of tube and radius of meniscus are two different things. But in one case they will be equal. In which case, try to understand this also. Similar type of diagram I am trying to draw here. If the radius of meniscus is, or the meniscus is hemispherical like this, that is the contact angle is 0 and the surface tension force will be in this direction, then radius of meniscus and radius of the tube both are going to be equal. If contact angle is 0, in many questions they won't give any information about the contact angle, then in such default cases we take theta equal to 0 only. And in this case, as radius of meniscus and radius of tube are equal, that's why we use this formula. This formula, we people don't pay attention to that part. Don't pay any notice to it. But it is one of the most important point in this part, that radius of meniscus and radius of tube, they are different and they are related in this particular way. Right? So I am summarizing it. When we insert a capillary tube inside the liquid, then due to the pressure difference, liquid will be rising up. Due to the surface tension force, liquid will be rising up, and this rising will be taking place until that pressure difference has been balanced by the hydrostatic pressure. We have solved in the earlier case directly by writing the pressure, and here in this case we have written by writing the NLM equilibrium equation. From that we got that height of the liquid in the tube is equal to 2s cos theta upon r rho g, wherein this r is the radius of the tube, or 2s upon r rho g, where here we are seeing r is the radius of meniscus. The relation between the radius of the tube and meniscus has been explained in this way. If theta is equal to 0, then the contact angle means when the contact angle is 0, the shape of the meniscus will be hemispherical, and here the radius of meniscus is equal to the radius of tube only. Now some more points we'll see. If theta is less than pi by 2, liquid will rise in capillary. We have seen H is equal to 2s cos theta upon r rho g. Right? Theta is positive, less than 90, this quantity is positive. If theta is greater than pi by 2, that is obtuse, liquid will fall down in capillary tube. Because here cos theta will be negative, negative sign is telling instead of going up, the liquid level will fall down, means it will be H 2s cos theta upon r rho g. Negative will come, negative means downward, and magnitude will be this one. If theta is equal to pi by 2, if theta is equal to pi by 2, then neither the liquid level will rise nor it will fall in the capillary tube. Liquid will neither rise nor fall in the capillary tube. Now, up till now, we have ignored the liquid contained in the meniscus. We have written only weight of this part. We have neglected the weight of the liquid contained in the meniscus. If the weight of the liquid in the meniscus is also to be considered, if weight of liquid in meniscus has to be considered, then what we have to do, S into 2 pi r cos theta is equal to pi r square h rho g plus the weight of the liquid which is in this part, means this is the meniscus, then this part of the liquid, say it is m, then m into g, right? And from here we will get the value of h. Sometimes what people say, assume this is hemispherical shape, so this volume people take it as pi r square into r minus pi r square h minus 2 by 3 pi r cube. This is considered as hemispherical. Then this is the volume of the liquid in the meniscus into density. This is equal to m. Sometimes as an approximation people use this also, but this is valid only when the meniscus is hemispherical. Meniscus is hemispherical. Considering the hemispherical meniscus, this is the mass of the liquid in the meniscus, which also has to be balanced by the surface tension force. This also you can write. Next, say you have similar to capillary tube type thing. You have liquid in a tub and you insert here, say, some two thin glass plates, you are keeping it like this, something like this way. This way, parallel. Then here the liquid will have the meniscus like this way. Then, and it is throughout, like if this is there, liquid meniscus in this is this way. If these two are the plates, here the liquid meniscus will be this way. Then surface tension force will act and liquid will rise in the capillary, in between these two plates. Let us say liquid rises up to height h and this length is say L. Then what is the surface tension force? Here I can assume it is contact angle is theta or contact angle is 0. I am taking theta, it will be more general, S. Now this is L, this is L. So the contact force will act SL, and this component will come to SL cos theta, and this will be balanced by this weight of the liquid. So 2L SL cos theta is equal to, weight is how much? Rho into H into L into, let us say this separation between the plates is D. This is the volume of the liquid in between the plates which have moved up into G. LL cancelled, and then we'll have the height of the water, height of the liquid in between the two parallel plates as 2S cos theta upon rho H. H we have to find only rho into G into D, where theta is the contact angle. If theta is equal to 0, then H is equal to 2S upon rho GT. Right? Very much similar to capillary tube type thing. This is not like the formulas actually, but I was trying to tell that how the questions similar to capillary tube are there. Right? Another point also you can take. Let us take similar type of thing. Liquid is there, and in this we have one solid tube. This is solid tube. No liquid can move inside. It is solid glass tube, you can say. And this is surrounded by hollow tube. Here it is opened. So when liquid is going to be here liquid, this liquid will enter and it comes up to here. Then due to the surface tension force, liquid comes up to here like this. Right? So if I see the top view, it is something like this, and liquid is in this region. Means surrounding this tube, liquid is there on all the sides. Now here I am assuming contact angle 0, that will be easier to write the expression. But if contact angle is not 0, we can write S into 2 pi r cos theta. If contact angle is 0, S into 2 pi r. That is the only difference. Now here, if we want to find by what height the liquid rises in between this region, in this solid tube and hollow tube, in this region liquid will rise. Up to what height liquid will rise, if you have to find that. Now you see, say the inner radius is small r, outer radius is capital R. On this outer one, force is coming S into 2 pi r, and on this inner one, force coming S into 2 pi r. This total surface tension force 2 pi r plus capital small r is balanced by weight of this liquid. And how much is the weight of this? Rho density pi r square minus r square area into h into g. And from here you can find out what is the value of h. H is equal to 2s r plus r upon rho r minus r into r plus r. This is cancelled into g. 2s upon rho into r minus r into g. So this comes. Now another thing also you can take. I'm expecting you are understanding these are slightly nice concept. Try to concentrate on them. If you are not understanding in one go, see them again. Now the next one, you take this thing. Let us consider a capillary tube in which liquid has to rise up to a height of 2s cos theta upon r rho g, or I can say 2s upon rho r rho g, where r is the radius of meniscus here. We are considering a capillary tube and liquid in which the liquid has to rise up to this particular height. But what happens if the tube is not of this height, this length? If the capillary tube is of insufficient length, then what will happen? Will the liquid will come out? Try to understand this point. This is also one of the very nice point. If we have a capillary tube like this, sufficient length, liquid want to come up to here, contact angle theta, height this, it want to come up to here. But say the tube itself is not of that much height. Tube is only of height less than h. Say it is h1. And if tube is of length h1 and h1 is less than h, then what will happen? Will that liquid overflow? No. Then no liquid overflows. Rather, what will happen? Rather, the shape of meniscus will change. Shape of meniscus will change to balance the weight of the liquid in the tube above the liquid level here, to balance the weight. Try to understand this. Liquid won't come out. It doesn't mean if this is only up to here that this amount of liquid will come out. No. What is going to happen, you try to see. I am making some diagrams on this side so that it will be very clear to you, right? When the tube is of insufficient length, liquid does not overflow, rather the shape of the meniscus will change. The liquid does not come out, the shape of the meniscus will change. And how the shape of the meniscus is changing, you see this. Let us say this is the tube of sufficient length. Then here the shape of the meniscus is decided by the contact angle. Depending upon the contact angle, the shape of the meniscus has been decided. It is like this. If the tube is of sufficient length, right? In this also little problem will come, because I'll draw the more lines, then it will become overlapping. It is the meniscus. Meniscus under normal conditions and sufficient length tube. Radius of this meniscus and radius of the tube are related by what I have written, r by cos theta. Radius of the meniscus and radius of the tube are related by this expression, right? But say this tube is of insufficient length, then what happens? Liquid comes up to here. After that, liquid won't come out, rather the shape of the liquid meniscus will change. In this way, then this way. It will become more and more flat. The shape of meniscus starts changing. It becomes more flat. It starts becoming flat. That is, radius of meniscus starts increasing. Now you see, radius of this is smaller than this, smaller than this. And if it is still more insufficient, it can acquire up to plane surface last. This will be the last limit. Plane surface will be last limit. After that, liquid won't come out. Other thing is possible. It may go this way also. It may go this way also. Shape of the meniscus can take this way. So the shape of the meniscus is changing, but the liquid is not coming out. Just imagine if the liquid is coming out, then how much easy it is to generate the energy. Take one beaker, top side, or at very height, whatever water things are there, water bodies, keep one pipe of insufficient length there, and water will start coming down. And when the water will start coming down, gravitational potential energy can be used to convert, get the kinetic energy, can be used to run the turbines, run the motors, etc. So in various ways that energy can be used. So water won't come out, rather the shape of the meniscus will change. And the shape of the meniscus will change in such a way that if you see this expression, H is equal to 2s upon r rho g for a given surface, given liquid, these three are constant. So the product of H and R becomes constant. So for the tube of insufficient length, we can say H1 R1 equal to H2 R2. Here these are the radius of the meniscus. Radius of the meniscus, and these are the height of the liquid in the tube, or you can say length of the tube column. This is about the tube of insufficient length. When the tube is of insufficient length, liquid does not come out, rather the shape of the meniscus will change. Right? Now one more thing, one more point that also will complete. Now you might have seen this particular observation also. On some wet surface, you keep one plate, plate in which you eat, that plate you keep. And after that, when you are lifting up, it's almost stick. Then you have to apply a more force too. Then you slide and then you can easily pull it. Right? This type of thing. When the two surfaces are having two plane surfaces are having some liquid drop in between it, then this liquid drop will spread over an area of the plate. Now this causes the pressure difference at these 2 points, and that pressure force due to this pressure difference is so large that to overcome it you have to apply a large force. Let's see this particular point also in detail. Liquid between parallel plates. We can also say liquid drop or liquid film formed between two parallel plates. Consider these two parallel plates. Actually, this thickness is of the order of less than millimeter, but only for the clarity purpose it has been shown this much. And this area, you can say a plate, some 20 centimeter square area, and the separation, this separation is only few fraction of millimeter, right? It is fraction of millimeter. Now when the liquid drop has come like this, then here that liquid drop takes this shape. I'll try to explain the shape. Here the liquid, and it becomes like this. Means something like this way. Liquid here, and it takes this type of cylindrical curved surface. Cylindrical, half cylinder, means like this way. And similarly here also. Now here then what happens? This is the concave side, this is the convex side. This is the concave side, this is the convex side. Here the pressure is P0, and say here the pressure is P1. So P0 minus P1 is equal to, now here the radius of curvature of this part, like this is like this. So this cylindrical surface radius is d by 2, and in this direction the radius is infinite. So S 1 upon R1 plus 1 upon R2. This is R1 and this direction is R2. Then you got it as 2S by D. Now to lift this plate, here the pressure is P1A. This particular area, I am considering this area as A. And from the outside, we have atmospheric pressure. And to lift it, we have to apply the force F. To lift it, we have to apply the force F. Then F plus P1A is equal to P0A. Then required force to lift this plate is equal to P0 minus P1 into A. F is equal to 2S by D into A. So that's all for now. This completes the theory part of the surface tension. We'll discuss the questions from the next video.